Great. Thank you so much. It's my great pleasure to be here. So I'm going to talk about what we call signed rectified flow, which is, I think, an interesting extension of rectified flow for incorporating negative constraints into flow generative models. So what I will do is I will give a really quick recap on rectified flow, and then I will go strictly to the idea of signed rectified flow. So this is going to be a short talk, so feel free to interrupt me for any questions. I don't actually have lots of slides to go, so don't worry. So briefly, the idea of rectified flow is that you build interpolations, and you causalize the interpolation to get generative models that converts noise to data. So here, assuming you already sampled pairs of noise and data, x0 and x1. Here, x0 represents noise, x1 represents data, and typically these pairs are independent, but theoretically you can use any coupling. And then what you do is you connect these pairs using interpolation. Typically it's a straight interpolation, but you can do whatever you want, in fact. And then what you do is you causalize, in some sense, this interpolation process. Because the way built interpolation is you get the two endpoints and connect in the middle. It doesn't give you a causal generative models. And what you can do is kind of projecting this interpolation process into the causal process. And this is done by simply fitting the velocity field. You want to find the ODE whose velocity field matches the slope of the interpolation process as much as possible. As you can see that it's not, if the interpolation has intersections, it's not going to fit perfectly. As a result, you get this pattern where you have to, in some sense, rewire the crossings to get really well-defined trajectories for ODEs. This is what happens. And then, interestingly, this process can be repeated. In fact, if you repeat it several times, you will get these kind of straight flows, which is nice because you now, for the ODE simulation, only need to go to one step, simulate in one step, right? So this is the high-level picture. And the key property underlying this process is that when we convert the interpolation process into the ODE, which is a kind of Markovization process, but also you can sort of think it as a determinizing the slope. So here, whenever we actually feed the velocity field with this square loss, the analytic solution is actually the conditional expectation of the slope given each point. So whenever you have intersecting trajectories, you will actually get the average slope, right? So as a result, you get some sort of mean field approximation. A key property is that this process, even though it changes so you can view this whole thing as a transform from one stochastic process, which is the interpolation process xt, to another process, which is the ODE process zt. So obviously, there are different trajectories now. They have different joint distributions, but they actually have the same marginal distribution, and this is kind of well known. And because of this, it's actually a valid linear algorithm because you will get the same distribution as you have from the original interpolation process, right? And the underlying of this is this important continuity equation that characterizes the marginal distribution of the stochastic process given the expected velocity field, right? Okay, so another interesting connection that can be made is that this process, which we call rectify, actually monotonely decrease the optimal transport cost. So you can show that given any differentiable trajectory, xt, if you rectify and get a new ODE process and you just take the endpoints of the new ODE process, it always decreases the displacement cost for any given convex cost, right? So it's in some sense a Pareto descent on the set of all convex displaced cost. And further, you can, if you actually care, because this is actually universally decrease every cost, and if you care about optimizing specific convex cost, you can actually impose an additional gradient flow structure. So in that case, for the quadratic cost, for example, what you can do is you can modify this process to feed a gradient field rather than a generic velocity field. And what this will do is to remove the rotational components. And if you iterate this process, you will actually get the optimal L2 optimal cost. In general, you can actually get optimal C, any C cost, when C is a smooth convex function. So recently, Harry and collaborators actually had some analysis of this process and showed that this process can converge to the optimal coupling under certain conditions. Okay, so now that's the overview. But today I'm going to talk about an extension of rectified flow for incorporating preferences. So the idea is that in practice we have preferred data, which we prefer to generate. We also have forbidden data, the data that we hate, that we somehow want to avoid during the generative process, right? So this is obviously very important for safety constraints, for copyright protections and privacies and lots of other issues, right? So the question is how to extend the generative models to incorporate these preference information, especially for the negative constraints, right? A common approach is that we can use the idea that you have some reward function in some sense, and you exponential tilt your base function. This is what is typically done. And if you renormalize it, you get your exponential tilted function. And then you can try to derive what the flow model for the exponential tilted function, and try to develop practical algorithm. This seems to be a typical approach that has been widely explored these days. However, this formula has some constraints, limitations. One is that, curiously, if you want to avoid something, the best you could do is to put a zero probability, right? That's all you can do, because the probability are non-active. You cannot encode stronger, avoidance than zero, right? And because of this, I think that's a great difficulty in the learning settings. If you have noise, then if you have noisy distribution and you didn't observe anything, it could be either a missing information, it's simply missed data in that region, or it could be stronger prior that you want to avoid, right? So zero probability doesn't seem to encode or distinguish these two cases well, right? Another technical reason is that if you multiply two things together, you have to normalize the probability, and that just creates lots of difficulties, and lots of derivations will center around how to handle this normalization stuff, right? So can we avoid these difficulties? Well, it turns out you can use signed probability or negative probability, which is kind of weird, but it does provide a nice solution for some of the problems that exponential tutoring has. So now in order to encode the preference, I'm actually using a signed density. A signed density is simply, let's say, a density function, but you can take negative measures, right? You can assume that it still integrates 1, but you can have negative probabilities, right? So the negative values encodes how much you want to avoid that constraints, right? In particular, it does have some interpretation. If you put a really, really low negative value, it means that this is the point that I want to avoid really strongly, right? Versus if you put a smaller value, negative value, it means it might be okay to violate, right? And in particular, this negative magnitude, you can intuitively think as the debit, right? As how much positive information I need to add in order to bring this negative value up to 0, right? Exactly the idea of debit for negative values, right? And then, a simple way to construct a signed measure is you can actually mix two probabilities, but with this negative mixture. So let's say pi plus is the distribution that you want to encourage, and pi minus is the distribution you want to discourage. And then you build this extrapolation, right? So alpha represents the magnitude, right? So if the magnitude is high, you want to emphasize the negative preference over pi 1, right? Yeah. So obviously it's going to be weird because there's no way to talk about how to sample from a signed mixture, right? And the best we can do is actually sample from the positive part of mixture while ensuring by construction of the algorithm that negative regions will be avoided in a certain way, right? At this point, the problem is not well defined, but we'll try to explore what we can do with this tool. So the question is even how to define the problem and how to construct a practical algorithm out of it, right? Yeah.
My question is that you want to eventually use the expectation with respect to the signed measure?
Yeah. Yeah, eventually that's what I want to do. Yeah, that's right. Okay. Okay, so now just warm up. What if we don't actually have this weird signed measure? What if we have a typical signed mixture, which means that it's a convex combination of two distributions? In this case, everything is really nice. It's not really difficult to divide what happens in this case for flow models. And you can show that you have this formula where, in this case, the flow velocity of this mixture model is actually a weighted combination of the individual components. So Vt plus minus is the velocity field that you would derive if your target distribution is pi plus or pi minus, right? And correspondingly, the pi t plus minus is actually the marginal distribution of the interpolation that you build for the positive and negative things, right? So you can build these two things individually for the positive and negative components, and then you ensemble them together, and this will give you the mixture, the mixture velocity, right? So you can sort of see that it's simply a weighted combination. It's in fact a posterior expectation, because here you have your basically for each data point, you calculate how likely it belongs to pi plus and minus, and then you get the posterior average of velocity field, right? This is really nice. And do you guess what I will do next step? Yeah, just make it negative. This is what I will do exactly. So I will simply just plug this negative value, and I flip the sign. I get the same formula, right? That's it. So yeah.
Is there going to be possible division by 0 now? Because
yeah, it's possible. So you get a singular ODE. Yeah. Yes, you may feel guilty to do this, but physicists like to do something like this, where they get a formula and they formally continue it, extend it, right? In this case, as you said, you get a singular ODE. But curiously, you can still run this ODE anyway, because you can have a numerical solver. You can just solve this ODE anyway. And if you solve it, it does get something. It's actually pretty stable. You will get a stable trajectory. Everything is really nice. So singular ODE, in fact, it's a stably singular ODE, which means that the singularity is helping you stabilizing in the definition domain. So it's a still solvable ODE in most cases. So you can still run the ODE, right? And then you're curious what's going to happen exactly. And the rest of the talk is going to discuss what what's going to happen if we actually run this strange ODE, right? And one comment that I want to make is that the reason that this actually works, which I will show, is that as you are doing this kind of formal continuation, lots of important results still holds, at least formally, such as Tweedy's formula and continuity equation that we use all the time in flow matching and diffusion models. They still hold, right? So you will expect really good properties out of it. Okay, so now let's actually simulate this ODE and see what happens.
So just try to understand. So the V plus and V minus, you learn them separately?
Yeah, assuming right now they are exact. But in practice, we're going to learn them in a certain way. Yeah, we'll talk about that.
So these sign measures are similar to the notion of pseudo distribution in sum of squares proof technique.
It's certainly related to quantum mechanism. If you look at quantum mechanism, that's a whole theory built on top of negative probability, which you introduce negative probability and then everything becomes so natural. But I don't really understand that part of this physics. Yeah.
The other question I had is that is it possible to use the moments of this negative this design measure and generate sample to simulate the moments?
So what do you mean exactly?
So for example, if you have covariance
I see. Maybe in some special cases, but for now, for this algorithm to work, we need to know these quantities like Vt and pi t. Yeah, if we can estimate them, then that's no problem. Yeah.
How are you computing the densities?
Sorry?
How are you computing the densities?
How can I estimate the densities?
Yeah.
Yeah, I will talk about there are two ways. Let's say if you observe positive and negative data, you can use the density ratio estimation. So because here it only depends on the density estimation. So this is one way. Another way is that if you don't want to explicitly estimate density estimation, you can still actually solve them from the two velocity fields. So in fact, you can derive what ODE that the density ratio would satisfy given the Vt plus and Vt minus. And you can actually solve it. I will talk about that. Yeah. It's not the best elegant algorithm, I would say, because you will need to estimate these things. But yeah, for now, no worry about
You
it.
need some kind of like support overlap of the
Yeah.
points in time, because like V plus's velocity might not be learned along the V minus trajectory. So if you start evaluating like the V plus of X at an X that came from like the more minus trajectory,
Yeah.
you might not have actually learned the V plus velocity field like in that region of space if it
That,
wasn't in your training set.
that could be possible. Yeah, that could be possible. But if that's no probability, if that's no data outside of, okay, so your generative model will tend to assign zero probability anyway to the regions that it doesn't have. And now if that region happens to have negative probability, you will actively avoid that, right? So that's actually a simple case. But what's subtle is you have overlapping. Then you have a significant probability mass from the positive, and then you have to log that probability out explicitly. I think that's the struggle-ness for this algorithm. Yeah.
So, I think this is like negative guidance, but where you like the weight is somehow adaptive to where you are in space. Like
Yeah, it is actually. If you can actually formulate this as an adaptive guidance formula. I'll talk about that later. Yeah. Okay. So, any questions? Okay. So now we'll actually do some experiment and find out. And this is actually exactly what I figured this out. So I was curious about what's going to happen. So I actually solved this ODE, and I observed something like this. So, okay, so this is the signed measure, the target distribution that we have. And starting from a Gaussian, if you evolve the particles, you will get something like this. So these histogram are the particle densities, right? And this is the flow trajectory, how it looks like, right? So there are several observations. one is that you always get positive regions, right? Whenever the negative regions appear, there's no particle there, right? So that you always get positive regions. You can sort of see from here. And another thing is that within the region that you actually sample for, or within the region where you actually see particles, the density actually exactly matches the density of the sign measure. You can sort of see that histogram exactly overlaps with the density, right? And then you can see this truncation line really clearly, that somehow it's really doing some sort of truncation. So what's happening is like you have this sign measure, and then basically the flow is going to pick a positive subregion and sample a truncated version of that probability. So this is what's going to happen. Yeah. Okay, so yeah, I mean, obviously we're going to explain why this actually happens. So here's just another, it's the same plot. But let's look at this plot closely. So here, I'm defining this pi psi as the weighted combination, the extrapolation of the positive and negative densities. This is actually the sign density of the interpolation process, right? So, and then you can define this margin, this boundary in which singularity appears, because this is the part when the sign measure equal to 0. And it corresponds to singularity because this signed density happens to be the denominator of the velocity field, right? So whenever you approach this boundary, which is here, you will get singularity, right? And then the boundary always stops somewhere because you start from a positive density, right? So the boundary has to stop somewhere, right? And then what's happening is like you will evolve following the positive density for which nothing strange happens. And then suddenly some negative regions appear, and then the particle will actually follow the positive path, as if that's some sort of repulsive mechanism going on, right? Right. Yeah.
If I really refine the initial value, will some of particles actually hit region that are closer to the red part?
Which one?
So now it avoids the red part completely, right?
Yeah.
I mean, but you also don't have any particles starting in really.
Here. In the Gaussian case, you will be actually repulsive away. Because if you plot the velocity field, it will actually forcing it to be positive. But in general, it's not good. Like, if you have arbitrary coupling, then it's not guaranteed. But if you have a Gaussian independent coupling, then it's actually a stable process. So it will be repulsed away. This is just more plots showing that it's quite stable, actually. OK. So this actually answers your question. So for the case, let's say think about the simple case, the canonical case where you have the straight interpolation, x0 is standard Gaussian, and you have independent coupling. In this case, you can use Twitty's formula. You can apply Twitty's formula on both positive and negative, and then combine this formulation. And then you actually formally get actually exactly the same Twitty's formula for the sign measure, right? And you just need to redefine the derivative log pi to be derivative pi divided by pi, right? So this actually holds for both positive and negative values, right? It's only singular on the boundary, right? Right. Okay. Now, if you look at this, you can sort of see why it makes sense, right? Because the velocity field is actually trying to increase the density, right? If on the boundary you have really, really large gradient, you close to singularity, so this term is going to dominate, and it's going to be positive away from the negative side, right? So that explains one thing, which is why do we always stay within positive region? That is actually a strong force, right? Okay. So now look at this part more closely, I guess. The next thing I want to explain is why there is this buffer region. Because ideally, my first impression is, we should actually sample from the whole positive support, which means the particle should actually reach this whole part. But this was not the case. So I was trying to figure out why. So just some definition. So if you look at the sign measure, you can define the positive and negative regions as we already have, right? And then that's a different measure, which is the distribution of the ODE. So now you solve the ODE, you trace the ODE, now you get a distribution following the ODE trajectory. I will call this distribution pi t flow, right? So this distribution is always non-negative. It's a true distribution, right? And then, because it's always has positive support, so I'm going to define the reachable region of the ODE, which is essentially the support of the ODE process, to be omega r, right? It's actually a subset of the positive support. And then there will be another buffer zone near the boundary that the particle will never reach. So this is another part of the flow, right? As it turns out, there will always be a buffer zone by definition. This is because, as we already observed earlier, essentially we have this result. The empirical observation that we had can be summarized in this way, where the flow distribution equals to the signed probability constraint on the reachable region, right? So it's automatically normalized because you can see the histogram and the density actually exactly overlap. It's not like proportional, it's actually exactly overlapping. And by this constraint, the total probability mass of the reachable region has to equal to 1. And then as a result, you will have to have a buffer region to offset the negative mass. So if you look at this case, you can actually determine the boundary. The boundary is exactly the point on which the area of the buffer zone equal to the negative zone. Right? Yeah, right. So now this draws connection to continuity equation, because as I mentioned earlier, one of the key result was the interpolation process density equals to ODE density in the normal case. But now these two actually diverge, right? And they are diverging exactly in this way. So you can sort of see that the flow is actually picking a sub-region outside of inside of the positive region, right? Yeah. And in high-dimensional cases, this region is actually implicitly defined by the flow. So that's no analytic formula for it, but we know that whenever the flow reaches, you have this property, right? Okay, so why this happens? Well, this is actually a continuity equation, extension of continuity equation. So you still have, as I mentioned earlier, you still have the same continuity equation, because you can take the continuity equation for the positive and negative and combine them. By linearity, you can derive the same, that the sign measure actually also follows the continuity equation. The only special thing is that this sign measure is not a probability solution of the continuity equation. It's actually a solution that has signs. It's a sign measure solution, right? So, if you actually allow sign measure, the continuity equation actually may not have unique solutions. And as it turns out, in this way, the way to generalize the results of continuity equation for ODE is exactly that in the case of signed solution, the ODE that you derive from the velocity field has to satisfy this the same density but restricted on the domain. So it's a simple modification of the continuity equation, right? Right. Yeah.
This continuity equation has also a kind of Gaussian gradient flow interpretation.
Which interpretation?
So does this continuity equation have a Gaussian gradient flow or some interpretation gradient flow
Uh,
in space of sign measures?
It might, so flow actually in general doesn't really correspond to Wasserstein gradient flow. So I'm not sure exactly, but I would say this is really connected to optimal transport between sign measures. If you're familiar with that literature, that's actually some rich connection. Yeah. Okay. Any questions? But you can also, another way to interpret is that you can actually think this flow ODE is in some notion a really good, best approximation of the sign measure projected into the space of positive probabilities in certain notion of distance. But it's not important. Okay, so I need to speed up. But this is the physical intuition that I figured out of what's exactly happening. So if you flow the trajectory in this way, it feels like you're missing a part of them, right? You have parts of the region that have strictly zero probability. Now, what is exactly happening? Well, you can actually revert the time and see what exactly happens. So if you revert time, you start from this sign measure, and you can think there will be charged particles that emitted from the sign measure. So you'll have positive particles going from the positive region, negative particles from the negative region, right? So if you look at these negative particles, if you flow backwards, because this boundary is always closed, so the negative probability goes nowhere, and the only destination is to hit the boundary at some point. And this is because the noise source is always strictly positive. That's no way for the negative charges to continue all the way down to T0, right? And then for the positive charges, there are two possibilities. One is like, if it's really far away from the boundary, the trajectory will continue all the way down to the 0. And if you revert it, you get the trajectory that we actually see, right? Now, some other parts of the particles that are close to the boundary will actually hit the boundary. And when they hit the boundary, it will have to meet another negative charge particles. And these two charges cancel each other, you get nothing. And then in practice, you can see that these regions are missing. But if you are reverting the time, you can sort of see the collision of charged particles along the boundary. Right. Any questions? Yeah. So, yeah. Well, this is really just the same plot. Again, if you revert it, in practice we see nothing. But if you actually assume that's a mechanism to generate pairs of positive and negative charges with proper rate, you can sort of see the trajectory. You will emit pairs of positive and negative charges, and that will actually fill the missing region. If you have a mechanism to actually generate particles in this boundary, then you can actually perfectly recover the whole sign measure. But in practice, of course, it's difficult to do that, so we are simply missing that, right? Okay, so that's mostly what I want to talk about. I'm not sure if, yeah, okay, anyway. Okay, so now practical side. You can rewrite the ODE velocity field slightly, and you can sort of see that it has this extrapolation process that is very similar to guidance, like classifier free guidance, except that you have this adaptive rate. So typically in CFG, what we do is we have some positive and negative. Negative is, for example, could be the velocity without prompt. And you do this extrapolation with some constant rate. And this sign measure can be viewed as having adaptive measure, right? The adaptive measure is important because it's automatically adjusted so that you get the right probability, right? So if you are really already inside in the positive region, the lambda is going to decrease to 0 so that you sample from the positive region. And if it's close to the boundary, it will grow to infinity to avoid enter the negative region. So this is a comparison with CFG. So this row is CFG with constant lambda, right? And this is the signed measure with the adaptive lambda. And you can see that, you can sort of see that if you use a constant region, if the magnitude is really large, you basically get off the region because nothing is correct now, right? Versus if you use signed measure, even if you use really, really strongly positive, you will actually remain to be in the region of the positive mass with this nice truncated distribution, right? So we have some more plots just for fun. So it stably stays inside the region. Yeah. Yeah.
So my question is that, so in the classifier free guidance, they have unconditional score and they,
Yeah,
they
unconditional.
combine it with the conditional score.
Yeah.
So in a way that they are removing one of the mode of the data,
Yeah.
or you know.
Yeah.
So can we avoid this region of the margins? You know, if you want to, for example, just kill one mode of your distribution, or
Yeah.
you want to just sample from
Yeah.
one mode
Right,
and
right.
filter out the other.
Yeah.
So then this margin problem of, having this region that you had density but you don't see the sample, that disappear, right?
So in the case of CFG, we have the negative velocity is actually the unconditioned one. So it's the average over all modes, right? So if you use that as your negative one, you will actually amplify the current mode of the positive velocity.
You
Right.
filter out the other.
Yeah, you filter out.
Okay.
Yeah,
I see,
yeah,
I see.
yeah. Okay, so how to estimate the ratios? Now, it's actually an ugly thing. I don't really have super nice way, but one way is to, you get the positive and negative observations, you can estimate the density ratio. Or you can actually, if you are given the velocity, the true velocity field, you can actually analytically divide what this log ratio would follow. The ODE that will follow. It's a complicated one, but you can work it out and you can actually trace it. It actually works. So this doesn't require you to learn another model, but it's computationally expensive to some degree. Okay, so this is some application. So this is a standard result from image generation model, Z image. And then if you inject a negative pump, saying that to avoid this monkey mouse, you will get something strange. Looks working. And then here's the removing tree and glasses, and here's the changing the color. Right? This is another application where we set a negative distribution to be the delta measure of the training set. So in this case, we explicitly want to avoid the training set. And then in this case, if you generate samples from the base model and you find the nearest data point, you can sort of see that very closely you are recalling one of the data points. But then if you use the signed measure, you will actually posit way of finding different data points. Here's just FID for ImageNet. It seems to be improving. So here's another amazing example where we collect the positive and negative trajectories. But negative trajectories are the ones that are colliding into these blocks. And then we train two models, and then we use signed guidance. You can sort of see they will stay well inside the positive region while still keeping a magnitude of diversity. Versus if you use CFG, you will find if you use really large CFG, you get a degenerated trajectory, but still it doesn't seem to avoid the negative well. Okay, that's all. Thank you so much.
Yeah, for the test the image experiments, what is the negative distribution in that case?
Which one? ImageNet?
No, sorry, the removing red or like trees and grass. Yeah.
Oh, this is the same model, but with a negative pump.
Okay.
Yeah, let's say my pump is having red, having trees, and then you will remove that. Yeah.
I'm curious if so part of the problem that you never go into negative regions because you started with a Gaussian, right? So
Yeah.
if you also started with a signed measure, what would happen?
If you start from signed measure, I think what's going to happen is like you just decompose it into positive, negative, and then these are two different processes, and you can analyze them individually.
And is there like some promising application for doing that?
I'm not sure. So if you start from, for example, a negative noise, then you will actually flip. So basically, you're running the ODE, but with the pi plus and pi minus flipped. So maybe there will be some application, because that's a whole literature on optimal transport between signed measures. That might be something there. Yeah.
So my question is that suppose that you have this sign measure
Yeah.
and you generate from a distribution whose a real distribution whose first two moments are the same as this sign measure.
Uh-huh.
Because we can compute the second moment, first moment, and match them by one by one.
Uh-huh.
So then, can we, do you have any intuition what would be the shape of this kind of sampling, how it generates? If we do moment matching on top of sign measure.
So how do you do moment matching exactly?
So I take the moments of the sign measure.
Yeah, right.
And I use a Gaussian distribution to match.
Oh, to match it. I see. If you just match the moments, I think you will certainly get approximation. Like I think one general way to think about all this negative thing is like, once you construct a negative sign, the sampling problem can be viewed as some sort of approximation. So you find the best distribution to approximate sign measure under certain distance, right? So you can show that this flow, well, it's a trivial that if you just select the support inside the positive support, you will get one of the minimum on TV distance, right? So, and I think the flow is implicitly optimizing some complicated cost function, which is implicitly defined, right? So now if you use other distances, like moment distance, you will get other things. The only thing is like, you probably want something that is like a displacement cost, because that will preserve the support for you. If you use moment matching, it may not preserve the support. Yeah.
Maybe one question about this last sentence. So when you say it's one of the TV optimal, it's because the reachable region, I guess, is not specified?
Yeah. So if you optimize this, I think this is really a trivial result, because I think any solution of this form, actually, so any solution of this form where omega is a region of probability mass 1 inside a positive support is going to be a solution of this. It doesn't matter which region you are using because it's a TV distance.
Then do you have any understanding or characterization of what the reachable region is?
I don't actually have. It's implicitly defined by the ODE. I don't know exactly, for example, whether you will optimize L2. It's most likely not the case. So I don't actually know that. Yeah, so right now, this region, I don't have a good understanding. Yeah.
One last question.
If you just run the SD version of this, does it just not work? Or
SD version?
like you take the velocity field, but then you like use the SDE instead of the ODE?
Oh, using the SD ODE. I think it will still work. Oh. Yeah, because you have a really strong repulsive force. So it will dominate the, so basically you will have this and then you scale it and then add in some noise. And near the boundary, you still have this really strong force. Yeah.
All right. Let's
Okay.
thank Professor Liu again.